Okay, folks, I want to go ahead and talk about the direct substitution property. So this is something that we're going to be studying in the next class period, but it's sort of the big result, and I want you to start getting some practice with it. So we're looking at the direct substitution property. The idea is that in general, calculating limits is a very tedious procedure. It requires some very difficult steps in something called the epsilon delta proofs that we will cover in section 2.7. But what we'd like to do is, rather than doing those tedious steps, to come up with a sequence of general rules. The purpose of these rules, well, there's a number of purposes, but one of them is to build towards this direct substitution property. So undoubtedly the biggest result for this section is the direct substitution property. Okay, which we're going to look at here. Okay. These examples that I'm going to give you might seem a little bit strange, but I'm emphasizing some key points here. So if f is a polynomial or a rational function, and this is critical, especially for the rational function, and a is in the domain of that, then the limit as x approaches a of f of x, if you're being asked to evaluate the limit, it turns out that if a is in the domain of either the polynomial or the rational function, then evaluated the limit is the same thing as simply evaluating the function at the point. So in some examples you've looked at, you might have said, oh, boy, I did all this work to calculate a limit. I could have just plugged the number into the function. If ever that was the case, it meant that you actually could have used the direct substitution property. Okay. All right, so an important warning, and we're going to get some more practice with this. Students often assume that the direct substitution property applies to all rational functions, and this is not true. Specifically, if a is not in the domain of that rational function, then the property does not hold. Okay? Most of the questions, so if I'm going to ask a limit question, generally I'm going to be exploring some difficult portion of the function, something where maybe the function's undefined. So for that reason, most of the questions concerning limits of rational functions concern situations where a is not in the domain, and because of that, other techniques need to be used. So let me summarize what I just said there with this one example here, example 6, and then you'll get to repeat it. Okay. So let's look at this function here. It's a rational function. F of x is equal to x squared minus 1 all over x minus 1. So I ask you to give the domain of this function. Yeah, well, you guys have had some practice in calculating the domain. So hopefully we've seen that the domain is the set of all numbers x such that x could be any real number except that x cannot equal 1. So that's the domain in set builder notation, or if you wanted to in interval notation, it would go from minus infinity to 1, unioned with 1 to infinity. So you can give the domain either way. So now I'm going to ask you to compute the limit as x approaches 0 for this function. So we're looking at the limit as x approaches 0 of x squared minus 1 all over x minus 1. Well, what's the big result here? The direct substitution property says if we're dealing with a polynomial or a rational function and the limiting value, notice this is a, we call that the limiting value, right? And the limiting value is in the domain of the function, then if you're trying to evaluate the limit, all you have to do is evaluate the function at that point. So this step here, I'm about to apply it, is by the direct substitution property. By DSP, by the direct substitution property. This is just equal to 0 squared minus 1 all over 0 minus 1. Folks, what did I do here? Instead of trying to evaluate this limit directly, I'm simply evaluating the function at the limiting value. Why can I do that? Because 0 was in the domain of the function that I'm dealing with. So this cleans up to be just 1. In this case. So that's our limiting value. Okay. Now, it's very important that you contrast this example that I just did with this one right here. Okay. So here we're looking at the limit as x approaches 1 of the same function. So this is of x squared minus 1 all over x minus 1. And let me ask you, so in a second here, pause the video to answer the question. Let me ask you, can I apply the direct substitution property with this limit? So pause the video and think about that. Can I use the direct substitution property with this limit? Well, the answer is no. And why is that? Because 1 is not in the domain of the function. And for the direct substitution to apply, it's got to be a polynomial or rational function, and the limiting value has to be in the domain, which is not the case here. So I can't apply the direct substitution property. That doesn't mean I can't do this problem. It just means I can't use the property that we were just discussing. So instead, what can I do? Well, we've actually already seen this. Notice that I'm still writing the limit because I've not applied the direct substitution property yet. But what could I do? In this case, let's go ahead and factor the numerator. It factors as a difference of perfect squares, and we end up with this expression here. And we see that the factors x minus 1 in the numerator and the x minus 1 in the denominator, those divide out. So we're just left with the limit as x approaches 1 of x plus 1. Now, these two limits are equivalent by algebra, but let's look at this expression here. What type of expression is this? Well, it's a polynomial. And what did we say? For polynomial functions, we can go ahead and apply the direct substitution property because the domains of polynomials are all real numbers. Put another way, 1 is now in the domain of the limiting expression for this nice continuous expression, so we can go ahead and evaluate this through direct substitution. And we end up with 2. By the way, I used the word continuous just a second ago. We're going to learn that word later on, so don't worry about that now. All right, so at this point, you've got all the tools you need to do number 7. So go ahead and give that a shot.